Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about neural network detector for the MNIST digit recognition. So let's get started. In the last part, in part 3, we saw how to use a classifier network for the MNIST digit recognition. At this time, we will change our strategy and we will use a detector for the MNIST digit recognition. In such case, it makes sense to use a detector as in part 1 for the recognition, because it has the advantage that we can train the recognizer of each digit class to output a 1 or a value close to it when it recognizes its digits, or a 0 or a value close to it when it's not recognizing its digit. If no digit is present, all detectors will output values close to 0, which is something that the classifier cannot do. For that, we are going to use the same neural network structure as in part 3 for the MNIST classifier, but with a different loss function. Instead of the cross-entropy loss, we will use the mean-squared error loss. But we need to take into account that the mean-squared error loss expects a different target representation. For the cross-entropy loss, we need the class label number as a target, which means we have one integer or a float input digit. The mean-squared loss expects a float number for each class, which means 10 float numbers for each input digit, where the correct class should have a 1 and all other classes should have a 0. And then we can do this by initializing a torch array with zeros and setting it to 1 at the corresponding correct class, and this is called a one-hot representation. PyTorch has a function, it's the one-hot, that takes a long tensor with the index value of shape star and returns a tensor of shape star and num classes that have zeros everywhere except where the index of the last dimension matches the corresponding value of the input tensor. So it does exactly what we want to do. This is also an example from the machine learning mastery, but it was modified and translated to PyTorch by Professor Schuller to use a simple fully connected network, and I further ported and modified to run inside Jupyter notebooks. We start importing our usual libraries, so we are using NumPy, PyPlot, PyTorch, Torch Vision, and here we are defining the neural network model, and we see that we are using a very similar structure as we used before, and we have two fully connected layers. The first layer has the input features equals to the number of pixels, the output features also equals to the number of pixels, and the second layer has the input features equals to the number of pixels and the output features as the number of classes, like we did before. This time here we are using a relu after the first layer, so we're using the relu activation function after the first layer, and then we have the second layer and we return the output of the second layer. At this part again we are using 100 images for the training set and 10 images for the testing set. We are also defining the 10 classes according to the 10 possible digits from 0 to 9. And this is the same what we've done in previous examples. So in the beginning our example will print the one-hot vector ytrain one-hot, where we can see that each row contains the values for the 10 classes, and indeed only one entry is equal to 1 and all other are zeros. And this is what we are doing here. We are using the one-hot function and we are converting the target to the one-hot format. And here we see it was the original target 729908, and then here's the one hot format, and we see this is the first, so it's equivalent to 7, so 0, 1, 2, 3, 4, 5, 6, 7, and there is 1, 1 at the position. This is a 2, so 0, 1, 2, and so on. So now we've converted our target. It was a number, an integer that describes the digit, and now we are using the one hot format that also describes the digit, but we have a 1 at the position of the digit representation. Again, here we are flattening the images, so it was 28 times 20 by 28 pixels, and we have now 784 samples vector for each image, and we see that for our training set we have 100 vectors with 784 samples, and for the testing we have 10 vectors with 784 samples. So this is our training set and our testing set. We also did this before. Here we are defining our model using the network structure that we previously defined. Here we are using now the mean squared error loss, and the optimizer we still use the ADAM optimizer. At this point here we are training the network on the mean squared error loss using just 10 iterations like we did before. It's the same procedure here, and we have here the losses after every second epoch, and now we get also the final evaluation of the model, and we get the loss on the test set. It's higher than the loss on the training set, as we expected and as we've seen before. At this point here we are doing the inference like we did also in previous examples. So we are feeding our model with an image from the testing set, and then the model will predict, but this time using the detector, which digit it is. So this is the image we are feeding, and it looks like an 8, and the detector predicted that it's, yes, indeed, it's an 8. And we can look here, these are the values for all the classes, and here is the value for 8, so is the highest value, and this is with the argmax. We pick the highest value and predict the correct digit. So it's interesting to notice that now we have some values of the 10 classes, and we need to observe those numbers and we see if they show some confident detection. And finally, we are also feeding an image of random pixels as input, and we see that it's not a digit, but the prediction, our model thinks it's a 0, and if we see here, we have a value that is higher than this threshold for the confidence that we set, so the model thinks and predicts it to be a 0. So we need to be very careful in interpreting the results and setting correct thresholds. And of course, this is a very simple example, a very simple network architecture. We use just 10 iterations, but we can get a lot of interesting concepts and basic intuitions using this kind of simple examples.